All right. Hi, everyone. Is the volume okay? Thumbs up in the back. Good. And just checking on the font. Can people see the text all right? Do we need to make it any bigger? Just like maybe a little bit bigger. We'll try that. All right. Well, thanks for coming. We'll get started. We've got a 4-hour workshop today. This is the Xarray Friendly, Interactive, and Scalable Scientific Data Analysis tutorial. So hopefully you're in the right place. If not, stick around. It's going to be a good 4 hours. We've got quite a number of tutorials to go through, and we're going to be taking a break, just about like a 10-minute break once per hour. So you have an idea of where we're going. We'll get up, we'll move around. And if you need to walk out at any point, do that, because this is a pretty long session. We'll be here till 5:30 today. So yes, thanks again for coming. I'm Scott Henderson. I am a research scientist at the University of Washington. I've been involved in organizing this tutorial this year with several other collaborators, Deepak Cherian at NCAR, Jessica Scheik at University of New Hampshire, Najeen Sobani at NCAR as well, Tom Nicholas from Lamont Doherty, Anderson Banihirwe at Carbon Plan, and Don Setuan at University of Washington. So it's been fun putting this content together. This is also all kind of public content. So one thing we want to communicate through this workshop is that any of you in this room are welcome to contribute to improving the material we're going over or adding new information, especially content that is maybe relevant to your field of study or examples that you feel like would improve the usability of Xarray. So we welcome any contributions. I want to show kind of where this material lives online, just briefly, so that people can navigate this tutorial content. So on Slack, there's a link to this current page that I'm on. This is just a public web page at the Xarray tutorial website. And at the top, we have a banner that brings you to this page. So the tutorial.xarray.dev, as long as you're on that website, you should be able to get to this page just by clicking that top banner. This content is mostly Jupyter notebooks. So we've designed this to provide interactive code examples that you can modify. We want you to modify these examples, try things out with your own data sets, and experiment with the way that the code is written. But we also provide this rendered format so that you can just navigate the rendered notebooks and their outputs if you're having any sort of trouble with the computational environment. So for this particular workshop, we recommend using the Nimbari Jupyter Hub that QuantScience put up for this conference. There's a link there. Maybe just a quick thumbs up if people logged into that Nimbari Jupyter Hub. Excellent. There are other options for running this content. You can set it up locally. It's just something that we're not going to go over for lack of time today, but it's something we're happy to help you with either during the breaks or throughout the week. You should be good to go. Yeah. Also, as you came in, we were passing out sticky notes. These yellow sticky notes. If you didn't get one, are up front. And if at any point you're kind of stuck on something, if you put that sticky note on the back of your laptop, one of us will come around and help you out. So be sure to pick up one of those, and of course the Xarray stickers as well. So it is important as well, when you log in to Nimbari, there's an option to select medium instance for Xarray. So be sure to select that when you're logging in.
One thing to be aware of is that all of us now signing into that instance type, cloud auto-scaling is going to have to accommodate everyone signing in. So it's going to take up to 5 minutes. And churns, they cannot find those because that's the auto-scale video setting. But if it takes longer than about 5 minutes after you start that instance, that is potentially a problem.
Okay. So I'm going to walk through this next step, which is once you're in the Jupyter Hub, cloning the content that we're going to go over today, these notebooks that we'll be walking through. Okay. So once you're logged into Nibari, you should see a window like this. Maybe I'll make this a little bit bigger. Maybe not. So on our tutorial page, you can click a button off to the right here for this command to clone the repository where we have all these notebooks. File, new terminal, will get you to this terminal, and we'll paste that in. We are going to assume some familiarity with the interface we're using during this workshop. So we're not going to spend a lot of time going over Jupyter Lab. Hopefully this is a familiar interface to people. See some thumbs up. And again, if you're kind of needing some personal one-on-one help, just put those sticky notes on your laptop. So I have cloned that repository, Xarray tutorial, and it's showing up over here in the left. If you open that folder, you'll see a lot of subfolders, but we're going to navigate to Workshops, SciPy 2023, and there's a notebook called Index. When you open that notebook, you're asked to select a kernel, and there are these pre-configured environments for all these workshops at SciPy, and we're going to select the global Xarray environment. Then you should be good to go. So this index is kind of linking to our approximate schedule. We're going to stick to this pretty closely, actually. So right now, we're just going through this intro and setup. And then within this index, you have links to each of the notebooks we're going to be going over. So if I go back here to our web page, you'll also see down at the bottom an outline with links to those same notebooks. So at some point, if you're lost, if you're unsure what notebook we're at, you can use this page to navigate to rendered versions of what the presenters are going to be covering. So that's another option if you're feeling like you just want to follow along visually. And finally, I just want to show that because this is all kind of on GitHub in this public repository, it's pretty easy to edit or suggest issues with any of this content. So for example, with this indexing, selecting data, this is a notebook. The links up here at the top, there's a little GitHub icon. You can open an issue if there's a typo, if you found something unclear. This is a good way to kind of get involved in the content development itself. Or better yet, suggest an edit to the content. This brings you to the files that are on GitHub. So we'd love for people to get involved in this effort. I think one of the great things about Xarray, it's really fantastic software, as you'll learn today. It's also a good community of scientific users. And so today you're probably coming to this tutorial with more questions than answers, but at some point you'll find that you probably have answers to other people's questions. So definitely kind of get engaged in this online space, because the more the merrier. One other place I'll put out for that engagement is on the Xarray GitHub page. There's a discussions tab. So this is another great place to open up a discussion on whatever you're working on. We encourage people to post kind of publicly what you're working on so that others benefit from it. There is also the Slack, of course, for SciPy 2023. So throughout the week, if you're wanting to revisit some of this content or get in touch with us to work on things, please do so on the Slack channel. Okay, so with that, I think we'll get started with indexing and selecting data. So first notebook here, and Nagin is going to walk us through this. Thanks.
Thanks so much. Thank you so much, Scott. So yeah, today I'm going to talk about indexing and subsetting Xarray dataset and Xarray data arrays, and the ways that are possible for indexing with Xarray. One important thing is that since this is an intermediate tutorial, I'm not going to go over the details of all the different ways that indexing is available in Xarray. I'm going to go over them really quickly, but I'm not going to go into details of them. And then I'll talk about the advanced indexing and the Boolean indexing. So let's see, for this notebook, let's select the correct kernel, and then let's run all the cells. Okay, so Xarray have multiple different ways for indexing or subsetting your data, and you're probably familiar with them. So if you're familiar with NumPy, you know that you can basically use NumPy, a similar indexing as NumPy for with Xarray dataset or data arrays. So for example, this MP array is the data, the underlying data in this data array, in this Xarray data array, and you can use this indexing basically syntax for grabbing all the entries of the first index, the 20th entries on the second index, and the 40th entry on the fourth index. Similar position-based indexing or positional indexing is possible with Xarray, exactly similar. The only difference is that the output of this method of indexing with data array is a data array. So that's the only difference. There is another slight difference, which I'll talk about in the advanced indexing notebook. But with this method of indexing, it's kind of hard to know which axis is like time, which axis is latitude, which axis is longitude. So it's kind of like it requires a little bit of like mental gymnastics to remember all these things. So with Xarray, you can also use dimension names. So for example, you can, using the ISEL index select, you can use basically the dimension name. So for example here, regardless of if latitude is like axis 1 or axis 2, I just give it like latitude 20 and longitude 40, and then it will give me basically the data for that latitude and longitude index. So this is the ISEL. This is all good, but, and you can also do slicing with this, so you can say, give me the first 20 time steps of my data, or give me the first 20 entries of my latitude, for example. This is all great, but this requires you to know exactly where, the indexes for the specific elements of your data set or data array. So for example, if I want data extracted at a specific latitude, I have to know the index for that latitude. So another way for basically indexing with Xarray is basically using the select with the values or label-based indexing. So the label-based indexing basically provides you, so you can basically just give it like a latitude. So I want to get the values, or I want to get the data at 25 degrees and 210 degrees, and just give me those, and using the cell method, you can basically do that. So this is great and make things much easier. It doesn't require you to remember the indexes, and it doesn't require you to remember which axis is like corresponding with which dimensions. And you can also do slicing with this method. Again, I'm not going to go into the details of these. You are probably familiar with all these methods of indexing. We have the drop cell method that is basically for removing an entry. For example, if you want to remove a specific point from your data, you can use the drop cell. And it works exactly similar syntax, exactly similar way to the cell. But sometimes, for example, you don't have, sometimes, for example, you have like a set of like observational towers, and you want to extract the data for those observational towers. You don't know the exact coordinates of your model output data. So it's kind of hard if you don't know that. So Xarray using the nearest neighbor lookups actually make things much easier. So when you do the select, basically, or the cell method, you can use the method argument and also the tolerance to find the nearest point to a nearest neighbor, or nearest point to it. And there are different methods that basically you can use with this cell. And then you can also set the tolerance for it. So you can say, okay, so I want to find, I have this like specific tolerance. I don't want to find like points if it's like bigger than like this distance from my original point. So we put an example of it with tolerance as well. Yeah, go ahead.
Can tolerance be different for active?
I don't know. I don't think so. I know it can be daytime.
Yeah,
but
not at the moment, I think. Okay.
Yeah.
The only way you would achieve that is chaining the selection.
Yeah. So and almost all these indexing methods work similarly with data set as well. So in the above, I used the data array, and here this is the data set. So far, we've learned about subsetting for latitude and longitude, and also we talked a little bit about time, but we didn't talk much about like the date time indexing. So working with, like in our field, basically like most of the data is time series data. And the date time indexing can become really difficult or complicated if you do not have easier, basically, methods for finding the times, basically. So, for example, if your model output is like every 6 hours, it might require some, again, like calculations to find like the index exactly where, like, for example, like that exact time happens. So the Xarray datetime indexing makes things really, really easy. First and foremost, you can give it a time, a particular date and time. For example, here, this example, like January 1st of 2013, and like this hour, and the cell method will basically select that time for you. And that works great. Another important thing is that it can accept, like, for example, so the data that we have was every 6 hours, so four occurrence or 4 entries per day. So you can also like do DSL time and then give it a day. And then if you give it a day, the output of it will be 4, because we have like basically 4 time steps per day. So it will basically extract all the occurrences, all the hours for you for that specific date. You can also do a similar thing with the year, or also you can do a similar thing with the month and year, and you can also give it like the syntax like this. This should work as well. So there are a lot of like possibilities that are available. One really nice thing is that you can also do slicing So for example, give me the range, like for example, for 1 week of January 2013, give me the data. You can use the time is equal to slice, similar to how you do slicing with latitude and longitude. So that works as well. And then you can also give it a list of basically non-contiguous dates. So for example, you have I want like these specific dates. Just giving it the list, it will basically extract that data for you. There's also indexing. There's also more advanced indexing available with Xarray. So using the date-time accessor, you can directly access the components, the underlying components. For example, the year, month, day, hour, everything. Using the daytime accessor. So for example, here, we are selecting all points for July across all the years using the VS time, the DT, the daytime accessor, month is equal to 7. Similarly, for example, if I want the 15th day of every month, I can do ds.time.dt, the daytime accessor, and that day is equal to 15. And in the notebooks, we have some, I think actually these are not rendering correctly, but we have some exercises that you can go through them as well. But again, like the emphasis of this tutorial was mostly geared toward the advanced indexing. So I'm going to go over the advanced and vectorized indexing. So if you remember, I mentioned when I was talking about the NumPy indexing that Xarray indexing works very similar to NumPy indexing, except for this this tiny difference. So let's find the correct kernel. Make sure everything works. Okay. So one important concept that is basically one important concept that is I wanted to kind of convey today was the orthogonal versus pointwise indexing. So if we basically give Xarray a list and say, okay, so select the data from this list for me across multiple dimensions. So there are for example, let me give you this example. So select these latitudes and these longitudes for me. What it will do is basically it will do the orthogonal indexing, which means that it will think of each axis as an independent axis and do indexing across these independent axes. And this is where NumPy is different from Xarray. So for example, what Xarray will do is that it looks at latitude 2, longitude 1, latitude 2, longitude 6, and latitude 2, longitude 7, and etc. So all the combinations. So the output, if you look at the output, it will look like this because it includes all the 2, 4, 10, 13, and then all of them. So all the combinations basically for each latitude, and then all the combinations of the longitudes. So this is different from NumPy, because in NumPy, if you do a similar syntax, what happens is that it will find you the point 2 and 1, 4 and 6, and etc. So say, for example, I have a bunch of stations across my domain. I want to extract the data across all these stations. If I use a syntax like this, it will not going to work. It will not going to give us the answer that we expected. So I put an example here actually with this. So for an indexer, you can also here, this is a list, but you can also do a data array as an indexer as well. So here, I have these target latitude and target longitudes. And basically, these are the latitude and longitude of my stations that I have. And I want to extract the data for these points from my dataset, Xarray dataset. If I do this, it doesn't extract, basically it doesn't look at them pairwise. It will find all the combinations and extract that. So if you look at the dimension here, the dimension actually make it obvious. So we are not indexing subsetting across time. So the time dimension would be the same, but the latitude and longitude, you can see it's like 4 and 4. So we are basically subsetting a region instead of subsetting for our points. So then what's the solution? How can we subset for our points? Xarray provides us a method basically for doing this point-wise indexing, and that's where the idea of like point-wise or vectorized indexing come in. So here we start. So let's go through, yeah. So the vectorized or point-wise indexing of data array basically can be used to extract this information for each site or each stations that we have. So look at them like pairwise, like latitudes and longitudes of each point, and then extract that data. And for triggering that, the important thing is that you have to have a shared output dimension name. So here, instead of, so remember in the above, when I have like 2 data arrays, the dimensions very similar to the dimension of my original data array or data set. But here I'm basically defining 2 new data arrays with dimension of points. And now if I do this the cell method, so I am basically showing the lat points looking like this, and the long points look like this. And now if I do da.cell with method nearest, you can see that now it extracted like all times for these 4 points. So this basically extracted data for all of my stations for like at all points. So it's like a time series for each station basically. So this is how to achieve this point-wise indexing. And that's basically the difference between NumPy and Xarray. Go ahead.
Yeah. So is that just because the points is a different table? It could be any string there?
It can be any string.
As long as it doesn't match the existing.
Exactly. And if it doesn't have a name, so if I give it just a list, it will automatically assume it has the same name as the original data set. So I put an example of this here as well. So if you give it a slice or an array without a name dimension, it will assume that it's basically the same dimensions as the original data set. Yeah, here it shows it. So that's the trick to learn. I know a lot of like data analysis in Earth System Sciences overall require selecting points from the larger data set, the larger model data set. So this was the idea of like orthogonal indexing versus the point-wise indexing, and how NumPy and Xarray are different from each other. Are there any questions? I tried to also link the documentation, but the documentation is a little bit vague also on this topic. If not, I can go over to the Boolean indexing and masking. So,
Sorry, may I ask one question?
sure.
So, is there, if I didn't want to, is there a way for me to do it with just a list of numbers other than, without making a data array or the indexing to do point indexing? Like, is there a method that's not cell, that's like cell or whatever?
I don't know if there is anything. I think but I mean, you can also, if you are familiar with any other things. Yeah, I don't know if there is anything. And if you don't give it a dimension name, it will automatically assume, yeah. So the easiest way is like basically using data array as an indexer and give it this shared dimension name.
Sorry, the reason I brought it up is like in Xarray, there's the index and everything, so I thought maybe there would be something.
Yeah, there isn't. Yeah, there isn't yet. So the idea of Boolean masking or Boolean indexing basically is a concept of basically filtering values based on a specific condition. It's basically a mask of like true and false for like the points that meet that condition or does not meet that condition or criteria. And then Xarray applied that mask and filtered the data. So there are different capabilities with Xarray Boolean masking. So I'm going to go over them really quickly. So let's see. Actually, let's go through this notebook one by one. So for this notebook, I am using the regional Arctic system model data set. It's different from the data set that I loaded in the past two notebooks. Those were the NSAP data sets, the tutorial data sets. And the difference here is that if you look at the data set, the coordinates XC and YC basically includes the latitude, basically are the fields that includes the latitude and longitude of the data, but the X and Y basically are, which are the dimensions here, are just the logical dimensions, or they do not like include the values of the coordinates. So we can, we can go through them. So XC and YC are the attributes, and they just like basically includes the our latitude and longitude of the data. And here, the first concept that I want to introduce today is using VER. So far, we talked about the cell method and for subsetting the data, but sometimes we want the subset output to be in this original shape of the data. So for example, with the cell, as we saw in the past notebooks, what happened was that after we subsetted the data, the dimension was the dimension of the subset data. But sometimes we want to basically have something that's like the same size of the original data. Or sometimes we want to replace some values from our data set or data array basically based on a condition. So that's where the idea of where it comes from. So here, for example, this example shows, this example basically replace all the NaN values, all the missing values with like a specific number. Just an example, and you can see the shape. The shape is similar as the original data set. And the vary can be applied to a data array, to a data set, and also we can use the XR var method with a function as well. So here are more examples of using var to mask based on a condition. So for example, here I just want to mask all temperatures below 0 degrees Celsius. So that's how I do it. And I try to here just make two plots showing like how I masked this data. So we don't see it actually right now, but by default what happens is that these masked data are changed to the NaN values. Unless we give it a specific number as we showed like in the example above. So in this example, we gave it a specific number. So you can see how basically where worked for masking your data. And again, I'm not sure why the exercises are not showing previewing correctly. But there is an exercise here basically saying that using like the syntax so far, can you mask all the points or all the latitudes above 60 degrees north? And the answer for it should be available if anyone wants to try using it. But I can also go over it quickly. So you can use this syntax that we learned, da.var, and basically say, okay, so whatever it's above 60. As I mentioned above, var maintains the original size of data, but you can use the option drop is equal to true to basically drop those points or remove those points that are fully masked. So here, for example, we are using drop is equal to true, and you can see that it basically drops those points. Actually, it's not. Oh, yeah, it's. You can see it if you compare it with the above. It has like more, a lot more data points, whereas this is more zoomed in. And I just added, since this data was on basically since I didn't like the visualizations above, I added a quick visualization using the Cartopy map projections basically to show the data on real map. But technically we didn't have to do it. I just wanted to show it like how it will look like. And, oh, is it trying to download? Yeah, I think it might be trying to download a lot of data. But you can see it in the Jupyter books that are rendered in the Xarray tutorial. So it's basically a map of world with the data above or above like it's like above some degrees north. So you can use var with multiple conditions, and I'm not sure how long this is going to take. You can use var with multiple conditions. So say, for example, you want to combine multiple conditions and like subset a region. You can definitely do that. For example, here I wanted to subset a region over Alaska, and I basically defined the minimum latitude and minimum longitude, and then I subsetted the data using that. So here I defined my masks with the AND operator, and then I used the da.var and tried to plot it. So let's see what's, okay, so I think this might be taking too long. So Scott, is this one using the medium Xarray one? Hmm. Yeah, I think it's not using the correct, yeah. But if you use the medium instance for Xarray, these all should actually display correctly. We just actually tested it beforehand, and they were looking correctly. So oh, no worries, yeah. No worries about that. So, yeah, I think we have the rendered version here. So this was the exercise, and there you go, this is the rendered version. And after basically selecting the points over like Alaska using the da.var and using the two masks, for example, with here's the output, so the data over Alaska, for example. And here I made a similar plot, basically adding just the border lines and it basically just showing like how it looks like. So here I provided, this is mostly like a mental exercise. So what we did above, like using var, if we had the NCEP data set, we could have used the cell method for selecting a region. Basically, if we were loading the NCEP data set from the previous tutorial, and then we did latitude slice, blah, blah, and longitude slice, and then like giving it the range, it would have worked. But can we use a similar thing or similar method with our data set right now? And if no, do we know why? So I guess in the interest of time, I'll answer that question. But so with the NCEP data set, we have, so basically our latitudes and longitudes are, they're basically similar as, so with our current data set, with the RASM data set, what happens is that we have the XC and YC and X and Y. The X and Y are basically the logical indexes, and the XC and YC are the scalar fields that include the real latitude and longitude, or real coordinates of our data. So because of that, we cannot use X and Y, because basically X and Y are just indexes, and we cannot use XC and YC because XC and YC weren't the dimensions. So that's why we couldn't use this method with this data set. But with this data set, because latitude and longitudes were our dimensions, and also it includes the real value of our coordinates, we could have used the cell method. So this was just an example, and I mentioned above that this var method can be used with a function, with a data set, or with a data array. So this is an example of using var with a function. So this is a very simple function. What it does basically is that it converts from Celsius to Kelvin and then compare it with some threshold. And you can see using this, and then it basically like convert it and then apply that condition and then mask that. So this is how to use var with function. Another thing that we can do with Xarray, which is useful, is selecting value if they are equal or if based on a condition. So basically, you can compare your values with a set of values and say, okay, so if my like values is in this basically list, clip that or select that for me. So here, this basically select values that equal to 2 or 4, for example. Just a very simple example. And a lot of people use isin with var for indexing, basically. I think I have an example here for indexing by arrays that are not labels of an array. So let me show you. So did I put an example here? No, but for example, we want to say, let's remove the points that are in, like, say, let's go back to our observational towers that we have. So we have a bunch of observational tower, and we want to remove a few of them. So we'll say that whenever like our data set or data array is in this, like, this observations, basically sites, remove this, or where this is, where and is in, using both where and is in. Remove those. Oh, actually, there it is. Here, for example, this example shows it. So, for example, we have a bunch of observation sites with a flag of like the instrument if it works correctly or if it doesn't work. If it doesn't work correctly, it says if the flag is in like 1, 2, 3, 4, 5, which is like the instrument flag for like the device working correctly. Keep it, if not, drop it, and then this is how it works. So this is basically dropping it. Here I just created this flag randomly, and that's why it kind of like randomly like filtered data. But working with like site observational data sets, I noticed that there are a lot of them are using flags, and a lot of times we want to use these flags or mask our data based on these flags to remove if, like, for example, the device is not functioning correctly or something like that. So this was basically the idea of Boolean indexing or Boolean masking and how to use var and isin to do basically to filter your data and remove or basically mask your data or remove some points that you don't want to. So if you use the correct, let me see, let's see. Should I log out, debug and log back in? Let's see, stop my server. If you use this correct server, this medium instance for Xarray, these notebooks, all of them should have rendered correctly. So let me check that. So please feel free to go through these notebooks. I try to go through them really fast for the interest of time, but if there are any questions, I'd be happy to answer them. And there are exercises in at least 2 of these notebooks, not in the advanced notebook, but there are exercises available in both the indexing and the Boolean indexing ones. So feel free to go through the exercises as well. And yeah. Are there any questions? Are there any confusions regarding any points? I'd be happy to answer. Yeah, so actually this was how it was supposed to look like. Yeah. Okay.
So this announcement we're writing out, actually trying to publish it, we realized that the Docker image that Nabari is using a different row miss.
Oh, okay.
Yeah, it's rendering for some things, but they're not using the latest one. So the exercises might not render. So if you want to do the exercises,
Yeah, the thing is that, Don, we just tried it before the tutorial,
I
and then
didn't
he said,
see the exercises.
okay, yeah.
for that.
Yeah. Okay, so if there are any questions, I'd be happy to answer. Are there any questions? Okay, go ahead.
Yeah, I'm just a little confused, you know, when you do a plot, it's showing X coordinates and Y coordinates, which I think are just numeric indices, is that right?
Yeah,
And
so
then-
for
and
that,
then the latitude and longitude are sort of implied, which is basically tells that like a full array of data, is that right?
so let's actually look at that data set closely, and basically we can see how it works. So if we run this, and let's look at the DS. Okay, so you can see that the DS, there is this dimension, the X and Y that you mentioned, is just like the logical indexes. And then there are the attributes, which we don't want. Then we have the coordinates. So the dimensions, the coordinates, the attributes, and the variable basically is like our variable. So the coordinates, this basically includes the real values of our latitude and longitude. And here I can actually, so what I can do is do in, let's see, ds.xc.plot. So you can see how basically this is the X and Y, the logical indexes, and this is the value of our longitude basically, going from like 0 to 360. Similarly, if I do this for YC, this is basically going from 90 degrees to whatever, like 15 degrees, something like that. So the data here wasn't, so I think this is on a curved linear grid, and it wasn't like easy to dimension it, basically, like to have like dimensions that are exactly the same as the coordinates. But if it was just basically a regular grid, you could have easily actually had that. So this is, yeah, I think this is curved linear grid. And yeah, I tried to kind of make this point now by kind of plotting it, and the plotting didn't work. But yeah, so if you look at the plots of it, it will also make sense. So here what we do for plotting it, it was using basically the cartopy, like applying the cartopy map projection, and then basically transforming it based on that map projection. So.
Yeah, so is there, I don't even know if my question makes sense, sorry, I'm not used to geodata. But is there a way for me to plot latitude, longitude, color, you know what I mean?
What do you mean, like as a?
On like, you know, longitude on the x-axis, latitude on the y-axis.
So yeah, so this basically the plot that I created here with the cartopy, that actually had the X and yeah. So let's see, indexing, advanced indexing here. Or we. Yeah, I think we are not in the correct notebook. You're right. So here, yeah, here it is. So this is just latitude and longitude. So we basically just transform it and apply the map projection, basically using cartopy. That's what we did. So if you look at the grids, it actually they'll look kind of, if we just like added the grid lines, it would have like of the mesh, basically what we call it in models is the mesh file of like the model. It would have looked kind of funky. It wouldn't be just like regular, like rectangular grids that we are used to. And that's because of just the way the projection works. Yeah.
We'll take a break.
Okay, sounds good.
But definitely ask us questions during the break. You can stay here, get some coffee,
and hopefully we'll kind of figure out what's happening with the the rendering of the notebooks. Thank you. Hopefully it will work for the next notebook. Kind of was surprised when it started working for
Yeah, sorry about that. I didn't look at it either. I know you did.
I looked through, but I did not catch the error.
All right, everyone. Welcome back to the second hour of our Xarray tutorial. I think we are we recording? Yeah, we're recording. Sweet. Thanks, Anderson. Welcome to the second hour of the Xarray tutorial. My name is Deepak Cherian. I work at NCAR, the National Center for Atmospheric Research, and I've also helped maintain Xarray with a lot of other people for a long time. This second hour, we're going to talk about a topic I like a lot. It's called computational patterns. So if you go back to the index notebook, you should see computational patterns. Click it, and it should open up a notebook for you. Yes, and then select global Xarray. And then we apologize about the exercises. I believe this audience should be familiar with the pain of package versioning and depending on the latest things of everything. So if you go to the rendered website and you hit computational patterns, there's a few exercises here that you should have time to work through. So we'll keep that going on the side, computational patterns. So let's switch the view. So the idea for this kind of tutorial was, I did a version of this a year ago, and I called it Thinking Like Xarray. There was a very similar tutorial this morning called Thinking Like Arrays by Jim Piwersky. Could you raise your hands if you attended that one? 4, okay. No worries. But the point of that tutorial was that there's kind of this paradigm or style of thinking where you think about manipulating whole arrays at the same time instead of thinking on an element-wise basis. The upshot of that is that you don't write for loops. You handle arrays as a big piece, and this is, NumPy is in the array programming paradigm, and it encourages you, for performance reasons, to think about whole arrays, right? And there's the act of writing a for loop is very de-emphasized. This tutorial is about that same idea. about thinking in terms of arrays and the fact that a lot of times you do analyses that work on subsets of arrays. And so we're going to talk about different patterns that all work on subsets of arrays in different ways. The reason you want to think about these kinds of things, I really like the tools library. And it says that it contains dozens of patterns like map and group by. It's a good idea to learn a core set because the vast majority of common programming tasks usually falls into a very small number of patterns. And this is like my personal experience. And there are benefits. You have to learn to identify these patterns. You have to like catch yourself when you're writing them and then force yourself to use something new, but then the benefit is the code becomes more readable. I've usually found it's easier for future me to come back and see what I did, a lot easier to interpret. In theory, you can depend on well-tested and benchmarked implementations. Xarray still has bugs, but hopefully we're moving better. So yes, if you're interested in these ideas, go see this other tutorial that was here this morning. The goal for today's lecture is to learn what patterns are available. Learn that these patterns replace common uses of the for loop. The goal is to not write for. Identify when you're re-implementing such a pattern and then be able to make that map between what you're doing and what Xarray provides. At a high level, the way I think of Xarray and why you should use Xarray is that it allows you to leverage metadata to write more readable analysis code. And importantly, the metadata is stored with your data. Not in your head, which is how usually I came from a MATLAB background, and I would just have to know that the first axis was latitude, right? You just have to know this, or you find out the hard way. Xarray, you use things like dimension names instead of axis equals 0. Much better. You can use things like tick labels, so you can say, give me latitude equals 45 degrees, instead of saying, give me the 10th element of data. Who knows what that means a year later. So that's kind of the simple use of Xarray. Xarray also provides, like I said, these high-level patterns. These are rolling or sliding windows. Coarsen, which is like block windows that don't overlap with each other. Group by, which is my favorite. A couple of group by specializations, so binning and resampling, and then weighted. Can you raise your hands if you've used any of these? Rolling, coarsen, group by. A good fraction. Good question. I mean directly. No. All right, no worries. Well, then the goal for today is to try it out and then make sure you do it the next time. So you're going to start by just loading some data, setting some settings. It kind of doesn't really matter. This is our most common example data set. So it loads up air temperature over North America. There's a monthly one, which is I've used resample to change the frequency. And there's a single time step that is in data. So in data.plot, you get a sensible plot out here. But that's just to show you what we're going to start with. DA, this is the default data set. You should see something like 3 dimensions, a lot of timestamps, lat and long. All good. Here's all the metadata that we like. So identifying high-level computation patterns. So here's a bunch of code. We'll look at this for a while, but it says, here's a bunch of months. I'm going to do a for loop over months. I did some filtering. I did some computation, in this case, a mean. I appended the data to AVG temps. That's a list. And then here's what you get. You get a list of numbers back. Raise your hand if you've done something that looks like this before. Yeah. Do you know what pattern this is? Oh, it's on the screen. Someone whispered it. It's the group by. Yes, exactly. Right. So this is such a common pattern. Like most analysis is something like this, right? You do a for loop, you filter out your data, do something with data, and then you stitch everything back together later. A very repeatable set of steps. So you could do that loop with group by, but here's a better way to do it. You could say group by time.month.mean. Some details there, but the point was all of those 8 lines are now down to 1 line, and I can come back later, look at it, and say, all right, I split my data into groups where each group had all data for a single month, and I took a mean, and now I know what I'm doing. And so that was, in particular, the group by pattern, is that when you see this filtering step, For things like sliding windows, you will usually see for loop and then indexing so that you're sliding along your data. Similarly, for coursing, you'll see block windows, which is again like an indexing pattern. So like a for loop and then an index, you should be thinking rolling or coursing. I will get to that in 20 minutes. There's a section exactly on that problem. Okay, let's see, what time is it? Okay. And so there's all these patterns. And so one way I like to think of this stuff is like index space versus label space. And here's an example of what that means. Here's data. Data is just a 2D array, lat and lon, right? And then as Negan just covered indexing, so sometimes you can work like this, which is 10th element along the first axis, kind of like NumPy. But you're kind of working in index space. You have not used the fact that axes map to points in latitude, or you have a grid. You've just said, give me the 10th point. You kind of have to know what the 10th point means. You can get slightly better, but you're still, you're saying, okay, give me the 10th element along the latitude dimension. But you still, like, what is lat equals 10? What point? It's latitude equals 50. You can see that if you did that, but you could also just do .cell, which works in label space. And so you're saying, hey, give me latitude equals 50 degree north. And it finds the right value for you, right? So this is how you would do it in Xarray, using the fact that you have all this metadata and you can work in label space. This is what you would do if you're working with just pure NumPy or MATLAB. You only have index space. You just always have to convert in your head two indexes. And the reason we just did that is that I find it useful to think of these patterns in both index space and label space, right? So in index space, the idea is that these are sequential windowed operations, and you're looking at your data in windows of a fixed size. Example is like a sliding mean. You could say, I want to take a rolling 10-point mean and slide it along my data. I could take like fixed length, but 10, let's say 10 indexes. The first 10 elements, then the next 10, then the next 10, then the next 10. So that would be coursing, where you're operating in fixed size. They're all sequential, and yeah, they're fixed sized in index space, right? So there's like, give me the 5 elements. I don't care what the spacing really is. Just give me 5. Question?
Is there a fixed size with label space? Or like, you want to do a rolling window and you have like unlimited time?
There isn't at the moment. It has been done. Pandas has some versions, I think. You can compose. In label space, Xarray only provides group by, and then you have to kind of map to a group by. The one exception to that question is resampling. So you can resample from, say, a daily data set to monthly, right? And so each month has a different number of days. And so that's a fixed window, but changing sizes, but you know that the output frequency is going to be constant, right? So that's an exception. But that's what I mean by label space. So that's something that's looks at the fact that, hey, I have date times. I know how to interpret these. I'm working in label space, right? And like each window is technically a different size, like 30 days in November, 31 in December. So windows are fixed width. The first function is rolling. So again, this is a sliding window. All of these patterns have common features. One is that you have all the common or standard reductions. These look like things like sum, mean, count, standard deviation, variance, etc. So here's an example. Here's what the data looks like. It's kind of blocky. I'm going to run a 5-point running mean along the latitude and longitude dimensions and make a plot. And that looks a lot smoother, right? So like I've slid through the data, averaged it out together. You'll see a little border at the edge. That's because you have to do something at the boundaries, right? If you want 5 points, but you're at the last point, you got to do something. By default, we just stick in nans, and I've told it to center it. Some details there, but they always support the common reductions. You always get an object back of the same shape as the input, and to do that, it pads with nans, as you see here, to make sure that you get the same size back. Is that kind of clear? Is this kind of stuff that people have used too before? I see some nods. It kind of comes from pandas. Yeah, lots of nods. Great. Good question. Yeah, like a stride. I don't think we support that by default, but I'll show you a function that can let you do that level of customization. So most of the time, you just want to do like a mean and like blah, 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 and it's easy. This lecture is about going beyond that, right? What if you want to do something custom that Xarray didn't provide for you already? So step one is reduce. And the key about reduce is that you give it a function that expects a plain array or a NumPy array most commonly. This includes many functions in SciPy and NumPy. Those functions expect NumPy arrays and they return NumPy arrays, right? And so in this case, here's an example function. It's PTP, which is peak to peak. It just takes maximum minus minimum, right? And what we want to do is I want to slide along my data and apply peak to peak. And so again, you express your rolling operation using data.rolling. I've chosen 5.5 and dot reduce, and I do numpy dot peak to peak and dot plot. And so the idea is there's a reduce method. You give it a function. It will apply that on all the windows and then give you back a result. Here's, hard to interpret, but you can kind of see North America. That was the answer. And so for this next bit is an exercise that isn't rendered very well. So if you go to computational patterns and you scroll down, sorry about this. Here you go. So this is an exercise. Just create a new cell in your little notebook, and you say calculate the rolling mean in 5-point bins using dot reduce. Right? And so I'll wait a couple of minutes. And again, if you have questions, if you're running stuck, just put up a yellow sticky note or raise your hand, and we'll help. Is everyone ready to see the solution? Just gonna nod. So hopefully this should be relatively understandable. So you create a rolling object, you call dot reduce, and you give it numpy dot mean. I showed you the one for numpy dot peak to peak. Right? So that was good. And so the kind of high-level goal here was to show you that there's a rolling object that kind of abstracts this pattern of sliding. It comes with a bunch of inbuilt functions, sum, mean, et cetera, et cetera. Sometimes you want to do something that's not already built in, so you can use dot reduce and give it a nice little numpy or scipy function that expects just plain arrays. Sometimes you want to go above that. And so the idea here is you can construct views of your data that kind of show you a sliding window. And so we'll get into this a little more detail. So here's a small, very simple data set that I create, data array. So it goes 0 through 10. I gave it a dimension name of time. It's a 1D array, and it's got 10 elements. Let's see, I'm going to turn it off now. And so if you call rolling times equals 5, a center equals true, you get this little rolling object. It kind of helpfully tells you that you want a sliding window that is 5 elements wide and is centered. And so it's going to do a little bit of padding to make that happen for you. And then it's got this very helpful method called construct, which actually takes a new dimension name. I'm going to click that so you can get this little view of your data set. So as you can see, I gave it a 1D vector of 10 elements, and I gave it a sliding window of 5. I told it to construct a new array with a new dimension name, window. You get back a 2D array, right? It's added this new dimension. The new dimension is named window, as you asked it, and it's got a size of 5, which is the same as your rolling sliding window length. And you can look at the values, and you can see these are 5-point windows, right? So it's padded with nands to kind of make that happen so that you're centered. But you've got 5 elements always, and you're kind of sliding along your data all the way to the end. So that the dimension along time is always still 10 elements, which is what you started with. And so to repeat, what we've done is we've taken this action of sliding through a data set or a data array, and we've constructed a new array where there's a new dimension that's your window, and it's kind of sliding along the original data. If you're familiar with NumPy, this is what's called sliding window view. That's exactly what's used underneath. But we're focusing on concepts here, and one is that you want to slide along your data set, and then sometimes you want to do something custom with it, and it's useful to look at this as kind of a reshaped data set. So 5-point windows, you added a new dimension, and now you can actually do interesting things with it. So there was a question up there about striding. So this is a data array. You can do all your standard data array things. Here, I'm going to write it as a little pipeline. I constructed it, and then I'm going to sell, let's say I wanted a 3-point stride for my machine learning thing. There you go. So is that clear? So it's still 5-point windows, but then I've moved every 3. So this is where, details. But sometimes details like these are not inbuilt, and what I like about these patterns is they give you a little way to pull out the underlying array in a useful form that you can then do whatever you want. Because at that point you have an Xarray object in arrays, and you can do what you want. So now there's a next exercise. So out here, which is use rolling.construct, and then use that to calculate the running mean. Again, you can just do So you should be able to start with this simple array, construct a 5-point running mean in time, but just make sure you go through the construct pathway and not just .mean, which would be the easy way to do it. So wait a couple of minutes. And again, if you have questions, please ask or put up a yellow sticky note. Someone will come help you. Also, just feel free to ask questions if something's confusing or. It's like applying a top hat filter. So there are no weights at the moment. So it's all just ones. So you could think of it, the dot mean, as convolving 5 ones. running through. Yeah. Is everyone doing well? If you got questions, raise your hands or put up a yellow sticky note. Great. Does someone want to shout out the answer? That's risky.
Main parentheses window, dot precision. Everything until now. The rolling time equals 5, and this is a window dot main window.
Sounds great.
But I don't. So I tried also access equals window, but like not very one of the yet. That doesn't work. So what is the name of the argument?
Dim for dimension. So we try to axis is integer and dim is name. So yeah. So you could have a dim equals window in there, and that would be clear.
Is there a way to change the boundary conditions so that it's not?
No, not really. It's a bit of a pain.
Okay.
Yeah, unfortunately.
There's more stuff to do in the print.
Yeah. So there's some details here. They don't really matter too much, but if you care, there's like a NumPy thing, a views versus copy. This is a view. It actually does something sensible for Dask arrays, if you're aware. If you don't, just forget about it. It actually works with rolling along multiple dimensions, but that's a little harder to visualize. Suddenly you're thinking of cubes that are sliding. It gets weird. But all of those things are possible. So that's it for the rolling section. So just remember, rolling is, if you have to do sliding window analysis, rolling is usually the object you want. It's got a bunch of inbuilt methods. If those don't work for you, it's got little entry points like .reduce and .construct that let you do whatever you want, possibly. The next little pattern is called coarsen. So these are basically kind of like rolling, but they're non-overlapping windows. So they're like block windows of your data. The syntax is basically similar. You get a little more control over the boundary conditions. It's basically the same as rolling. It's got supports all the common reductions, things like sum, mean, count, all of that. It does not return an object of the same shape as the input because you're kind of like decimating your data. That's another way to think of it. Unlike rolling, which always gives you back something of the same size, coarsen is going to decimate or reduce your data. A quick demo, here's data. It's a 2D array. The plot should be hopefully looking familiar to you. It's a little plot of air temperature. I say 5 and 5 point block coarsening. I tell it to trim the boundaries. So if you, sorry, I'm going to scroll up here. You see the lat, 25 is divisible by 5, so that's okay. It fits. Ln is 53, so it's not going to fit. So you have to do something with those 3 extra points. And there's options. I'm just going to tell it to get rid of it. That's what boundary equals trim means. And so if I just did the coarsen, again, you will get back a little object that has methods on it. It tells you that this is 5 points in lat, 5 points in ln. I forget what side is, but you can call .mean on that little object, and you can see it's decimated your data. You get 5 points back in lat, so that's 25 by 5. And in ln, you get 10, so that's 53. It trimmed off the 3, got it down to 50, and then did 10 windows. And so you get the answer. Yeah, I do have a plot, so if you can look at it, this is a very averaged picture of your data. It's hard to even tell, but it's like North America in there. So that's just what coarsen is and that pattern, remember? So like if you were for looping and then picking out windows of your data that didn't overlap, coarsen is your friend. Coarsen also supports reduce for reduction. So again, this is everything that we just saw for rolling just carries over. So that's our next exercise is use coarsen.reduce, but now you apply numpy.peak to peak, 5-point windows, lat lon. So yeah, I'll wait a couple of minutes. And again, if you have questions, it's a good time to ask. I'll emphasize that the API for each of these patterns is intentionally very similar. So like concepts you get for one kind of carry over. So rolling and coarsen are almost one-to-one. Like, it's just whether you overlap or you don't.
On the coordinate side, it's basically they could use the, actually we're not using them, but it's finding the center coordinate and lost and then, is that what you're doing?
I'm having trouble visualizing. So you're talking about coarsen, right?
Talking about coarsen and the fact that it returns a data set with slightly different longitude
Yes.
for the coarsen data, so it's just finding the center of that block based on.
I think that's right. Yeah. It's a good question. You have to assign some value.
Yeah.
I think it's picking the means. So again, there's this little exercise. Let us know if you have trouble. Use a sticky note or raise your hand.
Further that question, there's a toward argument in Xarray, so you can specify how you want to get from those labels to the labels. And it says it defaults to the sections. So you can have like maxes.
Thanks, Tom. Is everyone doing okay? Any questions? So the answer to this, hopefully, is straightforward. So I took my data, I did coarsening, I had to tell it to boundary equals trim, as I showed earlier, and then instead of just calling .mean, oh, this is a mistake, I should have put PTP there. Typo. Pull requests are welcome. So anyway, it should be just .reduce, and you can give it any numpy, scipy function, and it'll do what you expect it to. Good. And so we saw rolling.reduce, and there was construct.reduce, which is great. We saw rolling.construct, right? So you could construct this new data array. Coarsen has a similar thing. And this is like the second most asked question about Xarray, I think, is how you reshape, because there's no reshape method. The answer is to use coarsen.construct, and I'll kind of demonstrate that. So here's a new little fake array I made. It's supposed to look like a monthly time series. I mean, there's some code there, but let's look at the output. The one dimension vector, it's got time, 24 points, goes from 1 through 12, and then goes again from 1 through 12, so that's like months of the year, right? 1 to 12, 1 to 12. A common question is, how do I reshape this so that I have a new dimension that's year, and size 2 for this case, and then I have a new month dimension that is size 12, right? So 1 point per month, and then another dimension year. It's a common question in time series analysis. Well, I guess the answer is up here. So the way to think about that is that you want to look at blocks of your data. They don't overlap, right? So this is coarsen, and what would the size of that block be if you wanted to go from like month times year dimension? Any answers? It's like right up there. So the answer is 12, right? So you want to like go through your data. You say, I pick the first 12 elements, take that, and then I pick the next 12, and then I put it down here, and then pick the next 12, and put it down there, right? And so that's what course_construct does. So it gives you a new array. I told it to take the time dimension, split it into year and month, and this is the output. Does that make sense? Question? 30. Yeah, I think I actually, yes. I get to that next, kind of a non-divisible. Any other questions? Is that kind of clear about how we went from kind of a 1D time series to this kind of view that we wanted? It's a reshaping operation in NumPy, right? In NumPy, this is, so in NumPy, I would have, oops. Right? This is what it is in NumPy. It's a little more typing here, but you're kind of telling it, take the time axis and break it up into year by month. So like take all 12, and then take the next 12, and the next 12, and stack them together. So that's what it does under the hood. It's called numpy.reshape. Another useful piece is I started with a time vector that was just integers. It went from 1 through 24. That also gets reshaped. This is usually quite useful. So you go from 1 through 24, but it's being reshaped to 2D again. Yeah. Okay, so now for that question, like what if you didn't have like evenly divisible? So the answer then again is we kind of have to do this on our own. So I'm sub-selecting, so I took out one element. So instead of 24, I now have 23, not divisible by 12. And I have to tell it the boundary condition. In this case, I say pad. By default, it does nans. And then I do, again, the reshape. So in this case, it like stuck a nan at the end. Yeah. So is that kind of clear? You kind of have to handle the fact if it doesn't evenly divide, you kind of have to do manual padding, trimming, make a choice. It can get a little messy. So there's more material here. Definitely keep looking through it. I'm just going to move on in the interest of time. I'm not really sure what this next exercise was. Yeah, I'm just going to leave this for later so we can get to group by. But definitely look through this material when you have time. It's kind of useful. So the summary for the kind of index space, remember, we're working with windows of fixed sizes. So I think of that as working in an index space. So the idea is that you delete your for loops, look at them. If you have this kind of like, I'm sliding through my data, I'm looking at block views of my data, you should think of using rolling or coursing. Usually a good fit for your problem. They provide all the usual reductions as methods, so dot mean, this, that, dot mean, sum, count, all of those. But they also have these entry points where you can put in your own custom function like reduce and construct. Reduce lets you just give it things like a numpy or scipy function that expects bare arrays. Construct lets you construct a new or like reshape to a new view of your data. That then you can do anything you want with, so it's super flexible at that point. Okay. So for the next 10-ish minutes, we're just going to talk quickly about group by. And the reason I think of these as in label space is group by problems tend to have like one of two characteristics, though they don't have to. One is that they don't have to be regular sized windows. So going from daily to monthly is a good example. Some months have 30 days, others have 31, right? So that's not a clear coarsening. You kind of have to know something. And usually you look at the coordinate labels to know that, the date time vector. The other way, the other common group by problem is like the members of a group are distributed through your data set. So for example, monthly data, you can see like January occurs here, and then the next January occurs 12 elements later. And then again, 12 elements later after that. So, they can be like distributed through your data. Another common group by operation is something like histogramming or binning, right? And so that's when you like look at your data and you kind of discretize it and say like it goes into this bucket, that bucket, and they can be distributed kind of randomly through your data set. And so yeah, and so that's the reason I think of them in label space. They're not like sequential windows of, they're not windows where all the elements are sequential and they don't necessarily have a fixed size. They could vary. So I think of group by as basically a generalization of coarsening in some sense, not always true, frequently true. And so group by is kind of famous. It's kind of called split, apply, combine. It's this general workflow. You take your data, you split it into groups, like that little filtering for loop you did earlier. We apply an operation, commonly a reduction, and then you stitch everything back. Ooh, this one didn't render nicely. So there's this nice little image from the project Pythia, which I recommend you click on. We won't be looking at that notebook today, but I recommend that you follow that link. But it's a nice little visualization of what group by is. This is your input, where the different colors, in this case, represent 3 different groups. So there's black, red, and blue. You split it so that all the black elements are together, all the red, all the blues. You apply usually a reduction to get down to a smaller size, and then you combine them. So you have size 3. So that's how it's that's how it's usually presented, as this kind of neat split, apply, combine. In practice, I found that there's always like a first step, coming back to the question from the back from earlier, which is how do you identify those groups? This is like first thing. You have to label your data first before you can start grouping them. Sometimes it's easy, sometimes it's not so easy. And so for the next 10-ish minutes, we're just going to look at how to do that, how you like identify your groups or label your groups. And then after that, you can kind of do group by, and you can do all the kind of standard things. So here's the data. You can do group by time.month. This is kind of a shortcut. And it returns you 12 groups with labels. It very helpfully tells you 1, 2, 3, 4, 5, 6 through 12. And then you can calculate the monthly mean, just calling .mean. So like the standard reductions are available. Again, we'll talk about what's happening for that time.month piece. And so the reason time.month works is what it does is it translates that to, hey, data array, give me time.month. This is a little helpful shortcut. So if you plot what comes out of here, you'll see that it's a bunch of integers going through 12 and then repeating and going through 12. So it goes through the time vector and just gives you the month number. If you're familiar with pandas, this is copied straight from there. So if you looked at just time.month, yeah, it's a little hard because there's 2920 elements. But you can see like one that gets repeated at the beginning. The last month of data was 12, so it gets repeated a bunch. So that's the reason I did the plot. So you can kind of see that it's steppy, right? Similarly for binning, so in this case, I'm choosing to bin by latitude in like these, they're not uniformly spaced, but binning you can also think as a way of identifying groups. So like take an observation, figure out which bin does it map to. Resampling is also very similar. These are just like, it's more like coarsening, right? You take all the points in 2013 January average, then you take all the points in 2013 February and average, like go on and so forth. So it's again a group by problem. And so usually for constructing group labels, it can be sometimes easy, like time.month, but not always. So sometimes here's a useful list of functions that might help you. NumPy digitize is good for binning. Search sorted is like binning, but supports many other complications. You can click through. Pandas factorize is a very common one. It like helps you map integer codes to things like strings and characters and more complicated things. Pandas.cut, again, helps you binning. Datetime components is what we'll get to, things like time.month. Dataarray.isin is also a common function that can help you. SciPy NDMS label is also very cool. I just discovered this one recently. So the first one's going to be datetime components, and so this is the answer to that question. So there's da.time. This is a datetime vector, NumPy stuff. And there are a bunch of very helpful methods. So there's da.dt is what's called an accessor. You just think of it as a way to access properties of a time series. And so you can do .day. This is integers that are the day of the year, right? So we started in day 1 of January, so it's just a bunch of ones. This is a 6-hourly time series, so there are 4 in the day. So this is a bunch of repeated integers, right? And so you could think of these, if you wanted a daily average, you could think of these as your group labels. Like take all, if you wanted day 1 of the month, you just take all the elements that are day 1 of the month and you average them. And so you could do this as a group by, right? A shortcut for that is to just provide the string, which will give you the same thing. You can do more complicated things. .season is a common one in climate science, so it labels it at the standard Northern Hemisphere seasons, DJF for December, January, February, for example. And so, those are components. There's a big list in the documentation. Sorry, if you click there. Oops. Yeah, under attributes, you should see a lot of possibilities. And so you can construct a new array, you can even use the shortcuts, but basically that's a way of identifying groups is the kind of high-level point. Yeah. Let's see. So we're kind of running a little out of time, so I'm just going to show this one example where I create my own custom seasons. So the default .season is kind of interesting. So you get, let's see. You could do this, and you get these 4 is DJF, JJA, MAM, and SON. I do research in the Indian Ocean sometimes, and over there it makes sense to think of the monsoon season, June through September, as separate. And so I want these different ordering of seasons. One has 4 months, one has 2, October, November. So the default season doesn't make any sense, right? Like it doesn't apply. And so I needed to do group by. And so the trick here was I used, you can use the month. So I take the months, and then I want to create my own group label. So this is just illustrating that point that group by is easy to conceptualize as split, apply, combine, but you can only split once you know how to split your data, and that's usually where a lot of the challenges are. And so my solution for this was, let's take a look at the month as integers. I created just an empty array that we're going to assign to. And then you use numpy.isin. So if the month is in 12, 1, and 2, that's DJF, 3, 4, 5, March, April, May. 6 through 9 is June through September. And then 10 and 11 is October, November. Oops. And then I create that, stick that in a little data array. So here's my new Xarray thing. It's got a bunch of my custom seasons in there. And remember, I've used numpy.isin, very useful function for doing these kinds of labeling. And then I'm just going to do, here's my group by. I'm going to calculate the mean. I'm going to change the order of it. Group by gives you it back in sorted order. This does not make any sense. Seasons have a particular order. And then I'm going to plot it just to show what happens. So here are some averages. In the right order, DJF, MAM, JJAS, and then October, November. Right. So I wanted to do the same group by thing. I just had to figure out how to identify my seasons. And then I had to kind of dive a little deep to do that. It was a little painful, but I could still use the very helpful pattern later on, which is very useful. So now I'm going to kind of wrap up. So just kind of a quick overview. There's many other things that are useful. Definitely go through this tutorial. So there's things like floor, seal, and round on time, which is useful for grouping. STRF time is very useful. It has a very awesome website, which is how I figure out how to, what does that mean? No clue. Go to the website. It's very cool. Group by, just like rolling, also supports reduce, so you can play around with that. Group by does not provide a construct method because all groups need not be the same length. So you could see this could somehow backfire. You would have to add in a lot of nans or something in some cases. It could work very badly. But you can kind of do iterations. You can do a bunch of other stuff. Group by actually has a map method. Map is different from reduce in that map takes Xarray objects, returns Xarray objects. This is a key difference. There's a little example here where I group by time.month and then applying this IQR function. That IQR function is defined here. It calls .quantile, which is an Xarray method along the dimension time, which I passed. And so this is calculating the interquartile range. But It's meant to illustrate the fact that I'm looping over these groups of data and I'm applying a custom function. In terms of this case, I wanted my custom function to handle Xarray objects, so I used .map, not .reduce. You could write this with .reduce too, but just for illustration. So we zoom through at the end, but I'm hoping you have time to look at it in the next 10 minutes or later. This material is all on the website. To summarize, it's very common in array analysis to want to work on subsets of your data, and you're usually looping through your data. Anytime you're looping through your data, you should ask yourself, what am I doing? Are you working with windows of fixed width and sliding them along? That's the rolling window operation. Are you taking your blocks of data that don't overlap and just non-overlapping groups, and you're looking at subsets of your data in that way? That's a coarsening. It's very common for you to want to parse your data into groups and then do something on each group. So that's a group by. There are a couple of very useful specialized group bys. One is group by bins, so that's kind of discretizing, histogramming, binning, that kind of operation. Usually you do that with floating point values. You want to bucket them into little buckets. And finally, there's group by specialized for time axes, which is resampling and changing the frequency of your data. So you go from daily to monthly or monthly to annual and stuff like that, which you can also think of coarsening your data or a group by. The interface for all of these things is pretty consistent. You can iterate over them. We didn't really cover that, but it's possible. You can look it up. You can apply functions that accept NumPy-like arrays with .reduce. So we saw that with peak to peak. You can reshape to a new Xarray object with .construct, so we did some examples there. And finally, with group by, you can also customize using .map, which is you give it a function that accepts an Xarray object and returns an Xarray object. So it's different from reduce. You could use it for a reduction, but you don't have to. You can do more things. So I'll stop there. And if you have questions, please raise your hand or put up a yellow sticky note. Happy to answer them. Thank you.
We'll take another 10-minute break, so you can get up and move around. Basically, 10 minutes will finish your task.
A very nitpicky question, but I noticed that the bins will right close when you try to solve.
Mm-hmm.
I wondered whether that was standard, and it's not in NumPy or Matplotlib, but it's only
It-
that way.
It's standard in pandas is the answer.
Oh, okay.
But you can customize it. Let's see, what did I do?
Yeah, it's not like a parameter, but
Yeah,
it's standard.
I'm not sure what I did wrong, but oh, it's lat, not latitude. Frustrating. Yeah, so this is where so they're right closed. You could do. Was it right equals false? Yeah, the syntax around this has changed a bit. But yeah, so now you're left closed. So, yeah. But it's the syntax for pandas.cut. Cut is what's used. So yeah.
Welcome, everyone. My name is Anderson, and I work as a software engineer at Carbon Plan. And I'm one of the Xarray maintainers. And for the next 50 minutes or so, I'm going to cover parallel computing with Dask within Xarray context. Okay. If anyone needs help with getting to this notebook, please raise your hand or use your sticky note, and someone will help you. So, again, the main topic for this session, for the next 50 minutes, is to talk about Dask and Xarray. And the goals of this notebook is to, by the end, to understand how Xarray objects, in this case, data arrays and data sets, fit into Dask collections and how they interpret with Dask. And then we look into some of the functionality that you may have seen or used in the past that transparently works under the hood and uses Dask when working with Xarray. So we like to caveat the usage of Dask by saying that just using Dask itself doesn't necessarily make any guarantees in terms of like how fast your computation gets. So if you've never used Dask, or if you've used Dask before, you may have run into use cases where you expect things to be faster, and sometimes there's some disappointments when that happens. And that's the caveat that basically throwing more resources at a problem doesn't necessarily make it run faster. And the same applies to Xarray as well. Okay, so for those who are not familiar with Dask, Dask is a bunch of things. And for this tutorial, we're going to focus on two pieces. That's the Dask array, which you can think of it as a drop-in replacement for NumPy. So instead of working on NumPy arrays that are in memory, Dask array behaves and feels like NumPy, but out of core. And what that means is that you can work with data for which sizes are larger than what you could actually fit into your computer's memory. And then the second component is going to be the scheduler. In this case, Dask provides functionality for running computation, and the scheduler executes what Dask calls a directed acyclic graph. So Dask will basically take computation, express them into a directed acyclic graph that then the scheduler runs. Okay, so Dask array. So again, it's a drop-in replacement for NumPy. It doesn't implement 100% of NumPy. So the things that, one, don't make sense in the parallel context. So there'll be some things that you may easily find that they don't work once you move away from in-memory data. And one way to think about Dask array, you can just think of it as a block, as a bunch of NumPy arrays. So take your NumPy array, split it into smaller NumPy arrays, and that's what Dask is holding on to. So the way you usually create a Dask array from scratch is by porting Dask, and in this particular case, we're basically specifying the shape of our array, but there's an additional piece, which is how we want that array to be chunked. So in this case, we're creating an array of ones that is 10 by 5, and then we're chunking it into blocks of 2 by 2. there's a representation here that will give you a bit of summary information on what's going on. And again, it's telling us the shape of the array itself, the chunk, the sizes, the data type. And in this particular case, Dask actually hasn't done any work. So what it's showing us here is what it's going to do. But right now, this data doesn't exist in memory. Any questions, comments, clarification? Okay. In terms of the chunks, so the question is about, I guess, this diagram here might actually be misleading in the sense that the chunks themselves, if you look at how they're specified, they need to be regular. But depending on how the shape, the overall shape of the array, you may end up having a chunk that is smaller than this. So in this case, let's see, we could, for instance, have a 3 by 3, for instance. Is that still part of, is that still? Oh.
So the chunks, the way that you're specifying the chunks, there is only one of many possible
Ways to, yeah.
So you can have different chunks if you want.
Yeah.
And that will sometimes arise from operations like forcing group finds.
Oh yeah, true. Oh, so the answer was that it's possible to have chunks that are of different sizes, and one way to observe that is as the computation or the array or the object itself goes through computations, the chunks may basically be manipulated in ways that the resulting array has basically different shapes. So yeah. So the chunks don't need to be regular. Okay. So again, this is just a lazy object, or a lazy array. But then we can do regular stuff that you would do on an array. Like for instance, you can compute the mean. And again, this will happen lazily. So nothing happens at this point. And one nice thing about the directed ASIC graph is that you can actually visualize what Dask is doing under the hood. Like in this case, this is going to give us a diagram. Let's see how long this takes. Yeah, what's going on? Because this shouldn't be. Don't know why this is taking. Well, okay. I think it's frozen. Oh. Okay. Okay. Sorry about that. So this is the directed ASIC graph that I was talking about. So in this case, you can see that we're starting with a bunch of chunks here, down here, And basically, one way that Dask works on these chunks is by basically doing many smaller computations over time and then aggregating the results of those. So think of like a list of 10 numbers, split them into groups of 3, and then work on each group. And then as you reduce, at some point, you basically do an aggregation of the results. So, so that's what Dask is telling us that it's going to do here. Okay, so this is still, for some reason, it looks like it's broken. But then, as I mentioned, this is lazy. So if you actually want the results, you then have to call compute. And that would actually go ahead and execute that task graph. And now we basically have the ones after running through like 3 or 4 cells. So that's that at core. That's what Dask array is. It's a bunch of smaller arrays, and the chunks is the atomic unit that Dask is working with. So usually you don't have to, at least if you're working with Xarray, you don't have to create Dask arrays from scratch. And we're going to look at how that works. So when you open a file in Xarray, by default, Xarray will assume that you want to work with NumPy arrays. But then there's a special keyword, which is, in this case, chunks. You can basically specify how you want the data from disk to be chunked when it gets to the in-memory representation. So in this case, this is our original data set. It has 3 dimensions. And what we're saying here, which is this is a dictionary of the keys are the dimensions. So we're telling Xarray, and Xarray is telling Dask how it wants each of the dimensions to be chunked. So we're saying keep the entire time dimension as one chunk. And then for the longitude, we're basically creating chunks of 25. And then for lat, we're using this keyword auto, which it will basically chunk it using the size of the bytes and some default chunk sizes. So what we get is something that still looks like the original Xarray dataset, but then there's only one difference, that now the coordinates are still in memory. At least that's a requirement right now in Xarray. But then the data variables, they are lazily loaded. So the data array now contains Dask arrays. So you can do, so if you wanted to see how those chunks looks like, you can call these chunks, which will return a tuple telling you how the dimensions are chunked. And one note here is that all variables in a dataset don't need to have the same chunk sizes along common dimensions. So in this case, we only have one variable, but if we had multiple, you could basically chunk them differently. Any questions, comments?
You mentioned about indices having to be in memory. In the case, like the previous case where you had a complex collection of stats and so on, that's basically the size of your data, right? So in those situations, you could able to take that's like any.
Yeah, so that's, okay, the question was, I mentioned that the coordinates here, as you can see, they are all still NumPy, or they're in memory. And if you happen to have, let's say, a coordinate dimension that is the same size as your data, and you wanted that to be lazy, right now, technically that's something that you could do, but then it's not supported in Xarray. So there's been some work to try to expand in that space where this restriction on the coordinates being in memory is something that you can work with. Yeah. Yes. Here. Okay, so if you remember, okay, so like right now, if you look at the dimensions of, our data array, it's time, long, and then we have a tuple of, so it's a nested tuple. In this case, remember we wanted the time dimension to be kept all together in one chunk. So that's what here this is. And then for longitude, again, we wanted 25. And then for lat, this is set to auto, which it's basically using some default value for in-memory representation and figuring out how to split that up. And so in this case, we basically have, this usually gets a bit confusing. Chunk sizes as well, which this will basically give you a dictionary, which, as you can see, it's similar to the original chunks, but it also tell you the dimensions that those correspond to. 25.
It's this question about non-regular chunking that we asked earlier. So it means a chunk along the longitude dimension. There's a chunk of length 25 elements. Then the next chunk has length 25 elements. Then the final chunk has length 33 elements.
Yeah. So yeah, basically that's, remember we said long, I think was 25. Yeah. There's 53. So if you take 53 divided by 25, you're going to get 25, 25, and then the last one is going to be 3. Yeah. So you could also have like 10, 10, 5, 3. So that gets into that question about that. Do these need to be like regular? Yes, please. Rechunk it. So there's a. So you can call chunk, and then in chunk you can then pass in a new dictionary. So for instance, if I wanted time to be, let's say 10, so that's what I'll do, and that's what the new results would look like. Any other questions? Yeah, so I'm going to repeat that. So someone asked, what happens if I want to rechunk the data? And I mentioned that you can rechunk data at any point by specifying the new chunking scheme. But it's recommended to keep this in mind when especially working with large data sets. If you already know what patterns, what access patterns your computations expect, it's probably better to specify that chunking when you open the file on disk. That way you don't have to reshuffle the data once it's read. Good question. So if you Google or you go online, you see this recommended chunk size of like 100, between like 100 and 200 megabytes. And the origin of that recommendation had to do with the latency when it comes to the cloud, because you can easily, so I guess you're trying to basically make sure that your networking, so when you request the data, let's say you might be working on this machine, but then data is coming from like a cloud bucket. You want to make sure that networking basically overlaps with your computation. And transferring 100 megabytes on most networks is quite fast. So the larger your chunks are, the more memory you're probably going to need depending on what you're doing, but also the longer it's going to take to transfer that over the wire. Okay. So at some point, you might actually want to get access to the underlying data, and there's a couple ways to do that. One, when you have a data array, you can call .data, and the .data will actually return the underlying array implementation, because Xarray can work with multiple implementations of arrays. So if it's a NumPy array, you're going to get a NumPy array. If it's a Dask array, you're going to get a Dask array. So that's what this is showing. But then if you actually want to work with NumPy, you can call the as NumPy, and that would actually load the data in memory. And then there's a dot values, which by default, that will actually trigger the computation, actually load the data in memory. So if you know what's the underlying array implementation, the recommendation is to use .data. That way you don't accidentally trigger computation if you don't need to. But if you want to access the NumPy version of the underlying data, then you just call .values, or you call the as NumPy. Any questions, comments? Okay. So again, so far everything is still the same. When it comes to computation, Xarray follows the Dask paradigm, which is lazily, basically do everything in a lazy fashion. Don't do anything until the user explicitly asks for the data to be loaded and computed on. So in this case, if you compute the mean along the time dimension, Xarray will figure out what needs to happen, and it will again give you back an Xarray object, but then the data itself is still not loaded at this point. So in this case, mean, it's going to be 25 by 53 Latin long, but then the data is Dask array at this point. If you call the .data, you see that it's a Dask array. We can visualize what that task graph looks like. So in this case, when we read the data from disk, it's being chunked in 3 chunks. And then when we call the mean, this is what's happening. On each chunk, we're basically calling the mean. And then eventually, we aggregate the means. And what we end up getting here is basically, if you look at the Dask graph here, we end up with 3 chunks, which are these 3. Okay, so again, the common theme, everything is still lazy, but at some point you're going to need to access the actual data. And so far we've looked at compute. Data compute, there's a built-in method in Xarray called .load, which underneath it's actually using .compute. The only difference is that .compute here is the .load here is in place, meaning it will trigger the computation and then replace everything with the results that it computed. Whereas compute, if you need those results later on, it will basically, you'll have to recompute them again. So it computes them and then throws them away if you don't save them to an intermediary variable. And then .compute in Dask, if you're working in a context where your cluster or the workers in your cluster are distributed, .compute would actually send everything to wherever your session is running. So in this case, you might be running on a cluster in Amazon, and your notebook is somewhere else, and you probably don't want to send all that data to wherever your notebook is running. And then there's a third option, which is persist. So persist will work like compute. The only difference is that it will persist things in worker's memory, not where the session, in this case, the session is where the scheduler is running from, not where the scheduler is running from. And that becomes useful, especially if you're working with large data sets that maybe you have access to more workers with more memory, and your local session doesn't have as much resources. In that case, persist will work like compute and then persist things on the workers. So if you need those results, the workers don't need to go through that same work over and over again. Okay, any questions? Okay, so if you've noticed, we use Dask and Xarray, but we didn't actually do any setup in terms of like the cluster. Like everything just worked, and that is because Dask as a scheduler supports a bunch of options, and one of them is to use a thread pool or process pool. In this case, it will basically use the resources that are available on the machine itself. But then in a lot of cases, you may want to basically run this computation over a bunch of machines that are not co-located or not even on the same, not even in the same data center. In this case, you could use distributed clusters, and if you don't have access to those machines, you can still use a version of distributed cluster that we run locally. And this is available through Dask Distributed, and it's called local cluster. And the idea is that you basically create a cluster, and then you connect a client to that cluster. There's a shortcut here. So if you call client, so we imported client from distributed. If you call client without specifying anything, this will basically create a local Dask cluster. And usually you can get access to this cluster object by calling the cluster. So in this case, it created a local cluster on this machine with 4 workers. It's using all the memory on this machine, I think. And we have 4 threads in total. So in this case, I can actually go here. Yeah. So in this case, we basically have 4 workers, and each has 1 thread, and Dask will then figure out how to distribute that memory across those workers. And again, in this particular case, all these workers are on the same machine, but they could actually exist on different computers. So once you have that client and cluster created, you can just do everything as before. The only difference is that now everything is happening. Missed it. Let me try something here. Okay. So with the distributed scheduler, you actually get a bit of analytics in what's going on the cluster. So if you haven't seen this before, this is a dashboard that is giving you a bunch of information about what's going on in the cluster. And there's this task stream, which you can basically hover over. I think it's actually. Yeah, that was fast. But then if you hover over individual elements, will basically tell you at a high level the function that was executed, which you can think of this as a single task and how long it took. And there's a bunch of information about the workers, the CPU and memory and data transfer. Let me go back here, maybe. Let's see if we can. This may not show, but usually, yeah, too many. You can also see the task graph being executed. Okay. Again, same API works with Dask arrays and distributed clusters. In this case, if you do a selection, this is done. Here comes this. Again, it's lazy, computer rolling mean, do a selection on that. And if and when you need the data, you just call .compute. You don't necessarily need to call compute all the time. It depends on what you want to do with the data. So another version of this would be you want to write it to disk, and that will trigger compute in the background. So if you look at what's happening here, we basically have like a bunch of tasks queued. We have this task graph here. As it executes, these nodes will basically take different colors. I don't. Oh, it's fun. Okay. That was even faster than I expected. Let's see. think it's actually done. Again, Xarray will basically handle the interface with Dask underneath. So you do everything as if you're working in NumPy arrays, and whenever you need the data, you can tell Xarray to do the computation via compute or load or persist or writing to disk. There's a bunch of other advanced use cases where you may actually need to basically work at a lower level, and we don't cover this in this tutorial, but if you're interested, it's all in the documentation. So if you follow that link, yeah, if you follow that link, you get detailed documentation on a bunch of other things that you can do with Xarray and Dask. Any question, comments? Yes. Mm-hmm. 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 So I guess the short answer is it depends. And somewhat longer version of that is the use cases where, like what you're describing, you don't have data dependencies. So you have tasks that you basically want to think of like a for loop where you're not needing to access data from previous iterations. In that case, one way to speed that up is basically do the setup and then run everything in parallel. So that's one thing that Dask would be really good at. So you have, basically you have a single unit of work that you basically want to do multiple times. That's number one. Number two, there are cases where, okay, so a good example of what is Dask not suitable for is if the data all fits in memory, then probably don't need Dask. I would say look at Dask after you've explored all the other options. If your data fits in memory, there's no need of using Dask. Second use case where Dask makes sense is the data. You have a lot of data, but then you don't have enough resource. In this case, you can think of like, you could write like a for loop where every time you basically bring in memory, like a small chunk of the data, do some work, and then throw the results away or basically move on to the next chunk of your data set. And in that case, Dask is trying to do that in the background. So you could basically process a terabyte of data with only 16 gigs. At least that's what Dask promises that it will try to do. In a lot of cases, it may not actually work like that, depending on what you're doing, because sometimes you may want to hold on to some of the intermediary results. And over time, if you don't have enough memory, for instance, you basically accumulate a lot of intermediary results, and eventually you won't be able to go through everything if the server crashes. Yeah, it's doable. It will take longer. Yeah.
The next section of the tutorial today, we're going to talk about stuff that directly reflects. So there's there's this concept of core dimensions, which is in the tutorial documentation we have, and we talk about applying that Dask array operations along or not along these core dimensions.
Any other questions, comments? Are we good with time?
Okay, great. We'll take a 15-minute break now, move around, and we've got one more 15-minute session. So please stick around. We'll be back in 15 minutes at 4:30.
For a demo, I have this little notebook that just says running flocks on coils. Big data set, everybody's imported by
Yeah.
visualizations. It looks cool.
Yeah.
I'm only iffy because of coil for profits. It's probably fine, right?
Yeah. Is there a particular reason you're using coiled instead of just running it locally? Like you're running a classical cluster?
The alternative would be Dask Gateway,
Right.
but I
Okay.
don't want to spend my time setting it up.
Yeah. But, yeah.
It's kind of cool because it does group, I guess apply Yufeng does Dask, so it kind of ties everything together.
Yeah, I don't really think it's like a big problem.
I just want to like someone else to do it.
Yeah. I mean,
So I like lost 5 minutes on Good luck.
yeah. Wait, hang on a minute.
Change your
My kernel. Okay. Oh, confused. Okay. Okay, cool. And then where's the... yeah, okay.
But
Okay, so we're going to do the next section of this tutorial, the last section. I'm going to talk for about 25-30 minutes about how you can wrap your own custom computations with Xarray to turn janky NumPy code into beautiful Xarray one-liners. And this is like quite a deep topic. There's more material on this tutorial site than we will be able to cover. And we're going to reserve the last 20 minutes of this section of the tutorial for you to, hopefully, presumably, if you're an Xarray user, you have some computation that you'd like to apply to your data that's not just like typical means and maxes and things. So we're going to reserve the last section of time for people to have a go if they want to, and we'll be able to come and help them, is the plan. But what I'm going to talk about now should hopefully like lay the groundwork for how you might do that, how you might wrap your own custom computation and apply it in parallel, potentially with Dask. So almost all of Xarray's operations work on Dask arrays, and that's because Xarray is basically a thin, pure Python wrapper of NumPy-like arrays, and Dask can slot in where those NumPy arrays go. So when you do basic analysis, you're obviously calling methods that are in Xarray's API, but often you want to call methods and functions that are not directly in Xarray's API, but they are clearly sort of fairly standard forms of operations across arrays. So a simple example might be that in Xarray there is a variance method, but there's no skewness method, and that's just totally arbitrary. And skewness as a function clearly has a similar structure to variance. Like you could take an array of numbers and calculate like the single variance, that statistical moment, or you could take the array of numbers and calculate the skewness, or you could do the same thing with the kurtosis with a higher order moment. And at some point you have to like, Xarray can't support like every single method that SciPy has ever created or any domain specific method that anyone's ever created. But what we can do, and what we do, is supply the tools for you to wrap any of these types of functions yourself. So apply ufunc, which we'll talk about a lot in a minute, is Xarray's main way of allowing you to wrap custom computation. It is one of 3 ways that you can apply custom computation to Xarray methods. So the simplest thing you could do, which is kind of the non-Xarray way of doing it, would be simply to extract the underlying array, act on it directly, and if it's a Dask array, you might want to act on it with Dask functions. For example, Dask map overlap, Dask reduction. And then you could just wrap it back up again in a new Xarray data array object. And that would work, and sometimes that makes sense to do, but generally like you're only using Xarray like at the start and the end of that process. The second way of doing it is to use apply ufunc, which we're going to talk about a lot. The third way is this thing called map blocks, which is similar to apply ufunc in the sense that it's a way of mapping a custom computation across an Xarray object in a Dask-aware manner. But it is used for completely different types of functions than the ones that apply ufunc go for. So I think we're probably just going to focus on apply ufunc in the next section. So going to start with, so we're now we're in the advanced tutorial section, apply ufunc, gentle introduction. But I'm going to do this from the notebook so that we can exercise and we can execute things. So this is essentially what I've just said. So apply ufunc, this function we're going to show you, is so powerful that it's actually how most of Xarray works under the hood. So generally, like the most of Xarray's methods that you see, things like mean and max and standard deviation and so on, are really actually just calling Xarray apply ufunc and presenting it to you as like a nice little method. What we want to learn here about what apply ufunc does is we want to learn how it will automatically propagate the dimension names, coordinate variables, and attributes from your input Xarray objects to the output Xarray objects. It'll handle data sets, not just data arrays, by looping over all the data variables in your data set. And you can pass arbitrary positional keyboard word arguments that can go down into your functions, into your custom functions that you're applying. So let's start doing things. So we open our standard data set. So before we get to the full complexity of functions that need to act on like actual vector data, let's first consider a function that really just acts on like scalar data. So a very simple example would be like squared error. So this is like a point-wise or element-wise operation. You don't need to know, like when you calculate the variance, you need to know about all the numbers along a certain dimension in order to calculate like the result. But when you do the squared error, to know the squared error at one point in your array, you only need to know the value at that point in the array. And maybe you have two arrays, but you still only need to know the value at one point of that array. So let's define that function. So because of some magic hooks, you can actually apply this function directly to an Xarray. Oh no, we're actually just extracting the NumPy data here, applying it straight to the NumPy array. So we can see that this works when it's called on a NumPy array, where we've passed in a NumPy array with 3 dimensions as x, and we've passed in an integer as y. What we want to do is we want to apply this operation to the same data when it's wrapped in an Xarray object. So if we had extracted the underlying data from the Xarray object, applied it with the NumPy function to the NumPy array, we could wrap up the result manually like this. So we would be putting the result in as the data argument to the constructor of data array. We'd be putting the dimensions from the original object in. And the reason that this works is because the application of this point-wise operation hasn't changed the dimensions of the data, because we've done it for every element. We haven't lost any elements. We haven't reduced any elements. We've got the same number of elements as we had before, organized in the same way, so our dimensions are the same. So we could copy over those dimensions and reattach them to our result. So you can see we still have the same length along time, latitude and longitude. Similarly, we could copy across the coordinates, the attributes, the name. A shorter version of doing that would be simply to create a copy of the data set but replace the data within the data set. Copy of the data array. This is a data array object here that we've copied, and replace the data within it with the result. That's the fastest way that we could do this like manual wrapping, unwrapping thing. But what we'd rather do is we would rather directly apply the NumPy-like function to the Xarray object. And that's what apply_ufunc does for us. So apply_ufunc is this powerful function which we're going to talk about for the next like 20 minutes. And in this case, we are giving it our squared error, which is our NumPy x minus y squared function. And we're also giving it the arguments that we want to apply that NumPy function to. And these arguments can be Xarray objects or like simple arrays, basically. So in this case, what is going on? Apply_ufunc has effectively called squared error on the underlying NumPy array, but it's handled the automatic propagation of all the metadata, including the dimension names, the coordinates, and so on for us. So there's a sense in which it's basically like taken the Xarray object that we've given it, unwrapped it to get at the NumPy data, applied the NumPy function that we've given it, checked that the result is what it expected, and then it wraps the result back up in an Xarray object before returning it to you. And we can show that this is what's going on because we can, if we write a little wrapper function, we're basically just going to print at a certain point within the execution of this apply_ufunc to see what the situation is halfway through apply_ufunc being applied. So here our wrapper is just going to print the type of the array that is seen inside and the shape of the array for both the inputs x and y. And so you can see that when we call Xarray apply ufunc, then the actual function that gets executed, so we're still going to be executing the squared error numpy function, but it doesn't, this numpy function is being passed numpy arrays and integers, even though when we call apply ufunc, we pass it an Xarray object. So this is demonstrating that it's being unwrapped and the numpy arrays are what's being passed to the function that we provided. Yeah, we see the wrapper receives the underlying numpy array in the integer. So this is essentially what I've just said. Extracts the underlying array, passes the function, receives the values, and wraps it back up. By default, attributes are dropped because Xarray in general doesn't make a guarantee that arbitrary metadata attributes can be meaningfully propagated. For example, if your metadata said that you got your data from a certain satellite data source and then you did a bunch of analysis to it, that's no longer strictly true. So in general, those get dropped, but you can also just say, actually, in general, I'd like to keep them, and then you can use that keep hatchers in equals true to do that. Our example so far applied this numpy squared error function to a single data array, but you could also do it to a data set, and it effectively will just loop over all the data variables in the data set. So all this is doing is it's creating a data set with a second variable which has a subset of the data, so it's got a different shape, and it's been squared to just make the values different. And now if we do apply ufunc, you can see that the wrapper has been called twice. It's been called once on each data variable within the data set. And you can see that the result has two data variables in it. Okay, so the squared error function takes two arguments. But you can pass them positionally, which is what we've done, but you can also pass them as keyword arguments. So you can pass arbitrary keyword arguments to the underlying function. So if we passed y as a positional argument, but we could also instead say the keyword arguments that we're going to pass to our squared error function include the keyword argument y with a value 1, and this will work in exactly the same way. Okay, we need the next. Sorry? Mm-hmm. So this one is just what we're taking the error relative to in our, I could pass a numpy array here, I could pass 5. It has nothing to do with the dimensions. It just has to be a valid thing. It just has to be a valid argument to the squared error function at the top that we defined earlier, right? So y is being passed in here. So we're just doing x minus 1 squared. So it could have been x minus 10 squared, or if x is a 3-dimensional numpy array, y could have been a 1, 2, or 3-dimensional numpy array. Yeah. Okay. Tutorial pass ufunc. What's the next one? Core dimensions. Okay, so our previous example was deliberately chosen to be the simplest thing that we could have possibly applied with apply ufunc, an element-wise operation. But I've already mentioned other types of operations that are not element-wise. They have some notion of a set of elements that they act upon, or equivalently an axis of an array that they act upon. So I used the example of the variance, but an even simpler example would be the mean. It doesn't make sense to apply the mean to just a single element, to a single number. You have to apply the mean to a whole axis worth. And so we call a function that takes a whole axis like this and requires that axis in order to even like be defined, we refer to that as a core dimension. And so we're going to talk about this for a while because it's like critical to understanding what Xarray is doing and what apply ufunc is doing and how to wrap your own computation. You need to be able to identify the core dimensions of the function that you're applying, and it will depend. And it's a function of the core dimensions are a property of your function rather than a property of your data. And we're also specifically going to learn exactly how those core dimensions are treated by Xarray apply ufunc, so that you'll understand what's going on when you call the function, when you call apply ufunc. And here's a better way of explaining it than what I just attempted. They correspond to the fundamental dimensions over which an operation is defined, i.e. the summed axis in numpy.sum. One way to think about core dimensions is to consider the smallest dimensionality of data that the function acts on. So you can't take a mean of a zero-dimensional object. That would be pointless. You just get the same number back again. But you could meaningfully take the mean of, it would be a valid operation. It just wouldn't be very useful. But the smallest dimension of data on which it might be worthwhile would be to take the mean of a one-dimensional vector. So you would say that the mean operation could have needs at least one core dimension to be useful. And very important note here, a good clue that core dimensions is needed is the presence of an axis argument on the corresponding numpy function. That's not a universal rule, but if there is an axis argument, it probably means that that's what is going to be the core dimension when you wrap that function up. So for example, if you find numpy scipy skewness function, it has like an axis argument for the axis you're going to calculate the skewness along. Okay. Let's load the same data set. Okay, so obviously we could just call .mean on this Xarray data set, but we're going to do it the hard way instead to learn how this works. So let's write a function that computes the mean along specifically the time dimension for now for a given Xarray object. So we have, the way you do this in NumPy would be numpy.mean with the axis number corresponding to the axis that contains the time data. And so we're going to note for now that the time is on the 0th axis. If we wanted to confirm that, there is this method on Xarray objects, getAxisNum, that shows that if we pass it the dimension time, it basically translates dimensions to axes for a given Xarray object, for a data array. So we could call, you can just call numpy.mean directly on the Xarray object. That's one way of doing this. And you would pass axis equals 0. But we want to instead do this with apply ufunc. So in this case, we're going to apply our ufunc. Ufunc, I should have said, is a universal function. It's like NumPy language for a function that consumes and produces array objects. We're going to pass the actual data, so this is going to be an Xarray object, and then we're going to pass any keyword arguments that need to go down to the function that we're going to call. So in this case, we're going to try passing axis equals 0 and see what happens. So we've got an error. Applied function returned data with unexpected number of dimensions, received 2 dimensions but expected 3 dimensions. And so this means that while mean did indeed reduce the dimension, we didn't warn apply ufunc that that was going to happen. So apply ufunc tried to wrap the result back up again after applying the NumPy operation, but we didn't warn it that when wrapping the result back up, it would need to expect a different number of dimensions coming out. We didn't warn it that one of those dimensions was going to be gone, that was going to be reduced. So the way we can do this is we can say, this is why we need to know what the core dimensions are, because Xarray apply ufunc accepts this argument input core dimensions. This is the core dimension of the input arrays, the input objects. So in this case, we're passing a data set. So we have one entry in this list, and then that data set, we have one core dimension called time. And this is getting us further, but we're still getting an error. So next error, size of dimension latitude was unexpectedly changed. And so let's try and debug this and see what's actually going on here. So we can use the same trick that we used earlier of inserting print statements in a wrapper around the NumPy function that gets called to see what's going on. So we're going to print the type of array that's received, the shape of the array that's received, and the keyword arguments that went in, and apply the operation, then print the resulting shape. So it's the same thing again, just using this wrapper instead. So now we can see that there's something odd going on here. The input array had shape 25, 53, 2920, and we expected the output to have shape 53. Sorry, yeah. Exactly. So the problem is here is that is also our second learning objective for the day, is that the arrays are transposed automatically by apply ufunc so that the core dimensions are at the end. And this is basically a way of like standardizing the treatment of the core dimensions. So in this case, it means that it gets fed inside. This is about to explain what's going on. Core dimensions are recognized by name because we gave the name, the time string to the input core dims argument. Apply ufunc recognizes that exists in the data it was given. It then transposes so that the core dimension is placed at the end. Then it applies the NumPy-like operation that you've given it, which means that passing axis equals 0 was not the right choice. We should actually be passing axis equals -1 because -1 means the final one, and our apply ufunc is automatically transposing beforehand so that the core dimension is the final axis. And this is useful because it means that our functions that we're applying don't need to be special cased for the sort of transposition of the data that's going in. Like whatever the order of the dimensions of the data that's going in, then they will be transposed in such a way that your NumPy function can go on.
What if there's more than one core dimension? Is that a possibility?
Yes. You could imagine in this case if we'd taken the mean, and we're going to come on to this, but like if you'd taken the mean over latitude and longitude or something, like but that can be a list. Like you can have a list of core dimensions.
And then you need to know about the order.
But they're still distinguished by name.
You need to know which of the two final axes.
Yeah, so that's why the core dimensions of the lists have order. And so you can tell it at one latitude and longitude.
Okay, and they are not in that order at the end of it.
Very good question. Oh, sorry. Mm-hmm. I'm trying to think of a different way of explaining it. It might become more obvious when we go on to other examples where we loop over the remaining dimensions, like because in this case, well, actually in this case, we've taken the mean along the time dimension, but in doing that, we've like if you imagine you have like a cube of data that's latitude, longitude, and then time. When we apply this function, we can think of it as having taken the mean along like many, many parallel sort of rows, and we've collapsed, we've reduced along that core dimension, but then our remaining two dimensions are like loop dimensions, which we'll come on to. We've essentially just applied this sort of conceptually in parallel. So we have a meaningful distinction between this core dimension that's been reduced and these any number of other dimensions over which we've just applied the same operation many, many times.
If I would choose my core dimension to be time with velocity,
Mm-hmm.
the way that I would calculate the mean is different. So instead of going along one directional dimension, I would say it should be plane.
If you gave it two core dimensions, yeah, if you gave the core dimensions as time and latitude, then yes, then the mean would be applying on like planes like that, for example. Yeah. Yes.
Yeah, the other one way to view the wrapper function, many array functions, is that they consume some dimensions and they create new dimensions. The looping that Tom mentioned is one reason one. The second reason is one is describe what the function does. It takes in two more dimensions, maybe totally deploys them like you. You could create a new dimension and send that back with the next one is not what output for. And to do a new function is transforming to make this a different function. So you have to tell how you transform it. So it can take for some x and y, which are either. Yeah. And so when you move the dimensions an array, so you need to get to the two. Yeah, you can do that.
Mhm.
And then you have to tell it that, hey, I lost the last two on this dimension, but I can give you a array of the next one.
I don't know what your like mathematical background is, but if you have, it's really like very closely related to tensor operations where you have indices, and if the index is repeated, you do the summation over it. Like it's quite closely related to that. So if the index is like a dummy index, then it's kind of like a core dimension, and if there's just like a free index that's still going to be in the result, it's like there's some mapping there that sometimes actually really helps to work out what's going on. Okay. So we were talking about the transposition to the final position, which is why we need axis -1. So now if we do exactly the same thing, but instead of axis 0, we use axis -1, now it worked. So we've successfully applied the mean function the hard way. Okay, so we have an exercise here. Let me go and find a non-messed up version of that. The bottom here, I guess. Okay, so exercise, apply ufunc to apply SciPy integrate traps. So that's the trapezoidal integration rule along the time axis. Are we doing these exercises, or should we just have a few seconds to think about it and then ask the audience? How do we want to do this?
I mean, it's late in the day. Raise your hand if you want to try out the exercise and you don't want to try it for.
So we got our teacher's pet over here. Okay. Yeah. So, all right, I'm just going to show you. So we've got to import the corresponding function from SciPy because we're going to need to pass it to apply ufunc. We pass it in, we pass the data in. If you're integrating over, when you integrate, you're gonna get rid of the dimension along which you integrate, right? If you integrate to find the area. So we expect to have a core dimension along which we integrate, and we expect that to be gone. So it's only going to be present, the core dimension is only going to be present on the input, and then we need to remember up the transposition, so the keyword argument should be axis -1. So hopefully you can see that there is a sense in which one-dimensional integration is like the same sort of type of tensor function that NumPy mean is and NumPy max is and so on, because the core dimensions are the same. Okay, let's go back. What's the next one? Handling complex output.
Sorry, can I ask one more question?
Yep.
I'm not sure if I missed it earlier, but why is core dimension so restricted?
It's the inner list is because there can be multiple core dimensions for a single array. The outer list is because there can be multiple arrays. Yeah. Okay, handling complex output. So we've still so far only done a fairly simple example. So now let's consider some extra generalizations. So the first one we're going to consider is what happens if there's a new dimension has been created. So there's a core dimension on the output. And then we're going to consider what happens if that core dimension is not the same size. It's changed size. So a good example of a function that returns something fairly complicated is NumPy's 1D interpolation function. So we should read this signature because it's a one-dimensional function, but it takes 3 arguments to begin with. And it takes the data that you want to interpolate. It takes the points, sort of the coordinate values along which the data lay originally, and then the coordinate values that you want the data to be interpolated to. It expects a one-dimensional array as input and returns a one-dimensional array as output. But because you're interpolating onto potentially a different number of points, it doesn't have to be the same length. So let's load up the data set again. And we've arbitrarily created some new latitude coordinates onto which we want to do our interpolation. And if we just call NumPy interp directly on the underlying NumPy arrays, we can see that that works. But what we want to do is we want to wrap this call up into an operation that can accept Xarray objects. So the interpolation operation transforms the size of the input along the input dimension, along a single dimension. So we're going to have a single core dimension going in, but we're also going to be adding a new dimension on the output, so we need to give that information as well. So we have input core dims, but we also need to use the output core dims argument to Xarray apply ufunc. So this reads exactly the same as for input core dims. And so we're going to call that lat interp for now. So this call to apply ufunc will now look like the NumPy interpolation function we're applying. So we've got to supply the function we're applying. We've got to supply data as positional arguments for all the inputs to NumPy interp. So we've got 3 different arrays here. We've got the new latitude positions, we've got the old latitude positions, and we've got the actual data that we want to interpolate. And because we have 3 different arrays going in here, we've got to say what the core dimensions are for all of these 3 individually. So our list here has 3 entries. And if we were actually doing like a 2-dimensional interpretation on every array, it would be like lat long, lat long, lat long, for example. And then our output is we're only returning 1 array, so there's only 1 output, 1 outer list here, and that 1 array has 1 dimension, which we're going to call the lat interp dimension for now. So it's a doubly nested list, but only with a single entry. And we have an exercise. So is this the right one? Yeah. Okay. Apply the following function using Xarray apply ufunc. It adds a new dimension to the input array. Let's call it new dim. Specify the new dimension using output core dims. Do you need any input core dims? So our simple function here is a weird one. All the function does is expand the NumPy array to have an extra dimension. So NumPy arrays can have dimensions of length 1, for example. I think that's what this is doing. And so it's just taking like a 2D array or whatever and making it, instead of like 10, 20, it's like 10, 20, 1. So Do you need any input core dims? You don't need any input core dims, but you do need output core dims. So you need to add, the new dimension needs to be mentioned. Okay. Any questions at this point? I should probably be stopping more to ask that question, but go on. Mm-hmm.
Yeah, I noticed that that's an error.
What?
Can you go back to the,
Yeah.
to do Castro? For the input coordinate of that cell, yeah, the new lat should have input coordinate lat underscore info. It sounds like it doesn't matter there if it was matter for it to later.
Hmm.
Yeah, it doesn't make that underscore info.
Yeah.
Is that clear? It's kind of a confusing point. Yeah, sorry about that. That was an error.
Yeah, and that just, yeah, okay. Hmm. Just happens to work in this case.
Yeah, that was one second.
Yeah, right. Okay. Next generalization, I mean, we're still using the same function, but imagine you want the output to have the same dimension. Sorry, yep, go on.
On the same error, just
Uh-huh.
to make sure I understand what happened.
Yeah.
It's because it's just a NumPy array and not a data set, is that right? If it had been a data set with a dimension with a particular name, it would match that.
Yes.
Yeah.
You erased that like this.
Yeah. Yeah. But it's the only check that it's done is that you've given one core dimension and it's been passed like a one-dimensional array, and it's like seems legit, so it like proceeds. Yeah. Okay, so if we wanted to help make this neater and not have this weird like lat interp dimension, then it might be a good idea to make sure that our Xarray output that comes out of apply ufunc also uses the dimension name latitude for our new latitude dimension. But then that means that we're going in with a latitude dimension that has a certain length, and we're interpolating that onto a new dimension that has a different length, but we're going to call it the same name. So we've effectively changed the length of that dimension. And that's something that we very much need to warn apply ufunc that we're about to do, or ask of it. So if we don't warn it, so what we've done here is we haven't said lat interp, we've just used the same name for the dimension that's going in and the dimension that's coming out that are different sizes. It will complain to us that the size of the dimension latitude on the inputs was unexpectedly changed. So that's a fairly clear error. And then it even tells us what we should have done instead. It says, only dimensions specified in exclude dims are allowed to change size. So if we look at what the exclude dims argument is, it's a set, and it's a set of core dimensions to exclude, and only these dimensions are allowed to change size between input and output objects, and that's what we want to do here. So same as before, but we include lat and exclude dims, and now it works. And the result has the name latitude for this dimension of new size. Okay? Any questions on that? Okay. An actual generalization now, returning multiple variables. So I'm gonna go to the end of this, and then I'm gonna motivate why this has anything to do with Dask without actually going through the Dask notebook, and then we'll move on to like maybe having a go at wrapping some of your own functions. Oh yeah, we have another little demo to show as well. So this generalization, returning multiple variables, So if you have a function, so we can wrap functions that consume multiple arrays or return multiple arrays. So a nice example of a function that returns a multiple arrays, but is still simple to understand is like a min-max that returns the minimum of the array you gave it and the maximum of the array that you gave it. So we're going to define our min-max function by using the numpy array.min method so this is going to be a numpy array, and we're calling the minimum min method on the numpy array object. Final axis to simplify later so that we don't have to pass that explicitly. And we're going to open the data set again. Now, when we apply this, then our input core dimension is still going to be latitude because we want to take the minimum and maximum along the latitude dimension, but we are returning a tuple of 2 arrays from this function here. And we need to tell it what the output core dims of both of those are going to be. And we are able to say, okay, expect 2 arrays, but actually neither of those arrays have any core dimensions by just passing empty lists here. And you can see that we've created 2 objects and we've printed one of them. The other one is also an Xarray data array. So we've successfully wrapped a function that returns 2 arrays given 1 array, and it's created 2 Xarray objects for us. Let's find this example, this exercise. So we presented the concept of core dimensions as the smallest unit of data the function could handle. Do you understand how the above use of apply ufunc generalizes to an array with more than 1 dimension? So to see if you do, try applying the min-max function to a 3D version. So we actually sneakily subsetted the previous example data set to be just 2D. But if it was actually 3D, then what would happen if you wanted to find the minimum and maximum value of temperature across all latitudes for a given time and longitude? The important bit being here, time and longitude means 2 dimensions, which means 2 core dimensions. I'm starting to tell you the answer, but so if we wanted to use that, the solution would look something like this. Have I got this right? No, all latitudes for a given time and longitude, sorry. So you specify 1 time and longitude, but all latitudes. Yeah, we haven't actually needed to do anything differently in order to support this. That was the lesson that we're supposed to learn here. So, because even if we passed like a 10-dimensional array, like as long as that Xarray data array with the 10 dimensions, as long as one of them is called latitude, we could still use apply ufunc, and it would still look for that latitude dimension, do the transposition so latitude was at the end, apply the numpy function, wrap the result back up, and give it back to you. So the fact that we've changed this from a 2-dimensional input array to a 3-dimensional input array, it handles that absolutely fine for us because nothing meaningful has actually changed about this example. Like the core dimensions are not different, and the data is still high enough dimensional so that it contains the core dimensions of interest. So in this sense, Xarray is basically just like completely handling any sort of broadcasting that's going on inside here for you, allowing you to, and this is nice because it allows you to write a function that will then be applicable to any sort of like valid Xarray object that it could take. Yeah. So, okay. I'm going to say one thing about the Dask stuff, which we brought up earlier, which is that there are other notebooks here which are really good material that I think you find very useful. And one thing they talk about is how the concept of a core dimension relates to the dimensions along which your data is chunked or not chunked. And that's the connection that you need to understand if you want to know whether or not you can easily like parallelize a given function with Dask across Xarray objects. So if that's something you're considering doing, I would go and look into that. I think we want to do this demo? Yeah. Any other questions before we move on? We'll have a bit of time for people to come and chat to us or like ask questions to the room or to work on things, but no? Okay, thanks.
Thanks, Tom. Sorry, this demo was not planned, so hopefully it works. While this is spinning up, do people have questions? Is everyone kind of tired? End of the day, yeah. Apply ufunc is hard. If you find yourself getting frustrated, remember that all of us went through the same thing. It is definitely, you iterate through error messages, unfortunately. That is kind of the model. Okay, so this is very last minute. Hopefully it'll work. But the idea was to kind of show you a demo of a lot of these pieces coming together to do like a complicated analysis. It's written as a blog post. It's going to be kind of funny. But we talked about group by today. We talked about apply ufunc, and we talked about Dask. This is going to put all those three things together. I had help from Kevin Sampson, who's a hydrologist at NCAR, which is where I work, and also Matthew Rockland, who's here if you want to talk about Dask stuff. So data set. The data set is called the National Water Model. It's very cool. It's sitting in the AWS Public Data Registry. It's stored as analysis ready, cloud optimized Xarray data, and it's pretty big. Kevin and his colleagues reached out a while ago saying they wanted to aggregate this data into county level statistics and were struggling with it because it's big. Each variable is 250 terabytes. And so they were struggling with it. And so aggregation to counties, that should remind you of group by, right? So now a group is a county, and you want to take all the observations in a county and average them. So yeah, so it's split, apply, combine, as we talked about it. Some more background details is the group by problem with Dask can be kind of complicated. I spent a long time thinking about this. I wrote a package called Flux. So the reason that's relevant here is that it took the group by problem and tried to do it for just the Dask array. So no Xarray, just the Dask array. Given some inputs, do the group by aggregation. And the way you use that with Xarray is to use apply ufunc, as you just saw, right? It will handle all the metadata propagation stuff. So Flux uses apply ufunc, and it's doing the group by problem, and it's using Dask. And just to kind of show off, let's see. So the data is sitting in the cloud. So what I'm going to do is open a Dask cluster in the cloud with the help of this thing called Coiled. Coiled is a startup. Matt's the CEO. It's very slick. You should talk to him if you're interested. So what it's doing is like spinning up stuff in the cloud here, right? I don't know. Matt, do you want to say something? Or?
Sure. Yeah. It's going to spin up for a minute.
Oh no. Ooh. Oh no. Credential errors. Oh. I thought I did, but maybe this is not going to work. I don't know. It was cool. It was very cool. Here's the data set. It was 250 terabytes. D Cherian? Yeah, I think so. All right, try it again. Al- Always try your demos before, no.
Please use a Twitter email. Get next up.
This could be quite bad. Now I need to log in.
This is really common though, right? Like, these tools are really cool, but actually like getting access to the cloud is really hard. And deploying things in the cloud is really hard. It's challenging. Like we show all these cool tools, we show how they can be used in all these amazing ways. You do that, they're like, wait, let's figure out how to do that, figure out Kubernetes. Like there's actually a whole other set of skills that are needed to avoid this problem. To go from like demo level to like reliable demo level, or like even in production. This is where, like, this is the pain that like Xarray and Geo people feel. They all these in DevOps and
Yeah, I don't see it. Too bad. Where did I lose it? If it did work, you would see a lot of scaling. You would see 250 terabytes that I subset to 6 terabytes, still big. We load up some county outlines on a TIFF. That was only a gigabyte, but you can see many, many points. I use this Flux package. It does the group by problem. It does the big aggregation. You collapse latitude and longitude down to counties. So it's pretty small output, right? It's a big reduction. You go from 6 terabytes to 60 megabytes. I would load it. Matt said it would run in something like a minute with like 300-ish, 200-ish workers, so you kind of scale out. What does that look like? Ooh, this bit should actually run. So I think, oh no. I actually saved the output at some point. Hopefully this works. If it does work, you should see like a nice interactive visualization of aggregate stuff aggregated into counties. So anyway, lesson of the day was to practice your demos before you show up. It's easier when your laptop is not used for presenting. But yeah, we'll see. Maybe it should come up. It should be going. Got my imports. It takes a bit, but hopefully you should see a map soon. But in the meantime, thanks for coming. Oh, there it is. Here you go.
Just to clarify, your data is in some AWS bucket that is not related to Coil and Coil grabs it.
Yeah, Xarray grabs it and then hands it over to Dask, which does the thing. The data is, yeah, there's a link here to the public data. Here it is. Whoops. And yeah, so that was 6 terabytes collapsed to a single map that is county level means of this particular field. When it works, it's very impressive. But it really shows you, right? You can think at a very high level doing the group by problem. You could do it on a big data set. You could do it in the cloud. You could scale out with Dask. You could, in theory, use GPUs. Negin has a poster on GPUs and Xarray. So this, you could do a lot of things. But anyway, Scott, you want to finish out?
Sure. Yeah, I guess that will conclude the tutorial. I know 5:30 is the cutoff. I've been here for 4 hours. So just want to thank you all again for attending. Thank Deepak and Negin, Don, Tom, and Anderson for presenting today. So appreciate you all for sticking with us, and thanks to everyone who put the time in for these tutorials.
Thanks, Scott.